Hey, space fans! Welcome back to our channel. Today, we're talking about the amazing fourth flight of SpaceX's Starship. We've learned a lot about this rocket, from how it flies to how it lands, and what comes next. We'll discuss the new star factory, the upgraded propellant farm, and the important data collected during this flight. Get ready for an exciting look at the future of space travel. On today's episode, the fourth flight of the SpaceX Starship is in the books, and we have just learned more about this bleeding-edge rocket than ever before. We know how it flies, we know how it lands, and we know what comes next. First off, we have some really important information that was discussed in the pre-flight show that deserves mentioning. Star factory progress. SpaceX confirms that Starship hardware is already built for the next several flights and that the new Star Factory production line will be up and running this summer. That unlocks several thousand more square feet of floor space and will increase the production rate significantly. They're still targeting that volume of one ship stage per day, and it was alluded to that Star Factory production will begin with Starship V2, so that upgrade is coming soon. Propellant Farm 2.0. SpaceX has spent the last few months since Flight 3 working on their orbital tank farm. They're upgrading from the big vertical tanks to lower horizontal tanks. Not only are these much less likely to be dented and mangled from the energy of a Starship launch, but the new tank farm is also allowing for a much faster propellant loading phase, which is critical with a fully cryogenic rocket because the longer it takes to fill, the more propellant you lose to boil off, and the more difficult it becomes to maintain ideal temperatures throughout the system. SpaceX is aiming for a Starship load time of just 40 minutes, and that's only 5 minutes more than the Falcon 9 with 10 times the amount of propellant. This is easy to overlook, but it's very important. Payload. The payload on Flight 4 is data. Something that the presenters on this live stream did a really good job of was managing expectations for Starship. Too many people want to jump ahead and start talking about payloads and deploying Starlink V2 and all of that stuff. But the fact is that the only thing these early Starship vehicles are designed to do is collect data. That's it. They're not functional rockets. Real operations will only come with Starship V2. In the spirit of data collection, SpaceX admittedly went ahead and sabotaged their own heat shield. They removed 2 tiles from the engine skirt just outside of one of the vacuum raptors just to see what would happen. They also placed one thinner test tile, which is being called an ablative secondary heat shield. Elon talked about this over the weekend. He says that these inner tiles will be used on Flight 5 as an underlying layer that backs up the primary shield. These secondary tiles are an ablative material made from silicone and felt, meaning they self-cool by slowly disintegrating to expel heat. Elon also pointed out in an interview with Tim Dodd that the ship's primary heat shield tiles are made of ceramic, basically the same thing as a dinner plate. It's going to take a lot of testing to find out just how susceptible they are to cracking and breaking, not just on a single reentry but on the second, third, and fourth. Adding that second layer is an insurance policy to preserve the ship until these answers are fully known. Later on, during a video game livestream, Elon also said that the primary heat shield tiles for the Flight 5 ship are already being replaced with a new design that is twice as strong as the ones used on Flight 4. Liftoff. Everything looks good. We did lose one Raptor a couple of seconds into engine ignition. It appears to have fired up and then very quickly flamed out, which is exactly what the ship's computer is supposed to do. If an engine isn't running at spec, then it gets shut down. Even looking at the very high-res, super slow-motion footage posted by Cosmic Perspective, I can't see anything blow up or any excessive fire in the engine bay. Just roughly comparing Flight 4 with Flight 3. Shout out to Farzad for making this up video, showing them all together. We can see that Flight 4 is accelerating at pretty much the same rate as Flight number 3. It's just a hair slower. It's also worth noting here that Flight 2 was moving significantly faster than Flight 3, which is probably SpaceX wanting to stress test their flame diverter with more liftoff thrust. Stage separation. I love the extra camera view that we got here because it shows just how much of a role the grid fins play in initiating that booster flip maneuver. As far as I can tell, SpaceX is using just the energy from the upper stage engines to push the booster into its flip, which is super efficient and greatly reduces the need for the reaction control thrusters. Boost backburn. This is where it becomes clear just how much trouble the booster engines on Flight 3 were having. They started having a slow staggered shutdown at T plus 3 minutes 40 seconds. The middle ring engines start shutting down one at a time, leaving 4 running for a moment all on one side until those all shut down together. Well, if you look at Flight 4, this had a quick symmetrical shutdown at 3 minutes and 47 seconds, then the center cluster of 3 continues to run for a nice gradual shutdown. It's possibly also worth noting that the Flight 3 booster slowed down a lot more during its boost back phase. The airspeed dropped to just about 300 kilometers per hour before it started to freefall and accelerate again. On Flight 4, the airspeed only dipped down to around 880 kilometers per hour, so probably running the engines at a lower thrust. We can already see the process of SpaceX learning how to fly this rocket and manage the power of these Raptor engines. Interstage separation. This is a cool view watching the hot stage ring float away during free fall. The section was held onto the booster with the interstage clamps that were originally designed to hold the ship and the booster together. That allows SpaceX to essentially dump the interstage ring once it's served its purpose. There's a good reason to do this. Weight reduction is key. This one ring is super chunky. It's built to withstand 3 rocket engine startups at point-blank range. I've heard that it weighs around 10 tons alone, so that helps with the landing burn for sure. The real difference maker here would be the weight distribution. Super Heavy was not built to fly with this gigantic steel hat on top. It totally throws off the vehicle's center of gravity. It also puts weight behind the steering mechanisms, which can't be good. So they let it go. We get this cool view of the booster's top dome with all of the plumbing and the actuators. I'm guessing those pipes coming into the top are for reintroducing the boiled-off propellant gas into the tank for the autogenous pressurization. Then our interstage ring makes a second guest appearance, or it could be a UFO. I wouldn't want to rule anything out. Landing burn. As the clouds come up, we can see the grid fins working hard to keep the booster stable. You can see the point where the wind starts to influence the flight path. The grid fins definitely have much more effect here than they did on flight number 3. The booster straightens out as it hits the cloud layer at around 1,200 kilometers per hour. Going through this frame by frame, just because I can, we get a landing burn startup that begins with the center 3 engines. Then one middle ring engine comes online, which is a little bit weird. It was potentially supposed to be paired with the failed engine. Then 3 more come up, then 2, and then 3, with one middle ring Raptor left blank. SpaceX was able to provide 2 additional camera angles for us. Here we can see the booster from the air as it initiates the landing burn. We see the Raptor spin up that releases that big burst of gas and then the engine ignition. As we pass through the clouds, we get a new camera angle from a floating buoy that gives us a pretty decent view of the explosion and fire in the engine bay just before splashdown. It doesn't seem to have had any negative effect on the landing procedure, but something definitely failed energetically inside the thrust section. We know that there is still a lot to be learned about these Raptor engines. They are incredibly complex machines, and getting them started is a delicate dance under extremely high pressure. Energy wants to flow from high density to low density, so if the inlet pressure from the turbopumps ever slows down even for a moment, all of that raging combustion can start moving up instead of down, and that's when things explode. Either way, we got our successful water landing of the Super Heavy booster. It appears to have even hovered nice and stable for a second before engine shut off. You can see the excess methane gas burning off at the base of the rocket, and it makes a slow tip over into the sea. Fantastic work. Judging from the relatively short distance between the buoy camera and the landing, the booster must have come down right where SpaceX intended it to. Something that you might not have seen was the view back at Starbase. At the same time that the booster was splashing down, the Mechazilla arms activated and closed just like a catch attempt. Even the water deluge system below the launch mount was reactivated for a short low-press burst. This also demonstrates that none of the ground hardware was damaged by the launch this time around. Elon has already said multiple times at this point that he wants to catch the booster on Flight 5, which is exactly what I want to see. After the first few launches, I'm not particularly excited by the takeoff anymore. It's a big rocket, it's cool, but the tower catch, that is something totally unprecedented and unpredictable and just so insane. It's the only thing that can top the spectacle of the dual booster landing from the Falcon Heavy mission, as far as I'm concerned. Over the weekend, Elon said, I think Mechazilla has got a decent chance of catching the rocket, probably, I don't know, 50%. He did clarify that a bit, though. I don't think he means that the catch attempt has a 50/50th chance of being successful, because I don't know what the consequences of a booster crashing into the launch pad would be, but probably devastating for the ground systems, I would assume. I think Elon means there's a 50/50th chance of conditions being good to even attempt a catch. This is the same thing that they do with the Falcon 9 when it comes in for a return to launch site. Elon said, the booster will come back. It will have an impact point that's out to sea, so it'll have to steer itself towards the tower with the catch arms. If the booster detects that anything's wrong, it'll suicide itself into the ocean. If things are looking good, it'll steer over to the tower, and the arms should be able to grab it. Even if Super Heavy is cleared for a tower catch on Flight 5, which Elon has also said is coming next month, It's just as likely to abort the landing as it is to go through with the attempt. Let's cut to re-entry. Again, comparing to Flight 3, there's obviously a lot more control over the vehicle. Luckily, the problem with the attitude control thrusters seems to have been an easy fix. We're also seeing a lot less debris floating around the ship. It was never really confirmed what all that stuff was, but I'm also noticing that on Flight 3, there were several missing heat shield tiles just in the camera's field of view alone. There must have been several tiles that had fallen off on other areas of the hull. We're not seeing that on Flight 4, though. Everything looks pretty well stuck down for now, at least. Moving deeper into the atmosphere, Flight 4 has now outlasted Flight 3. The ship is continuing on a slow and controlled re-entry path. They're using the giant body and the displacement of the ship to help it fly on a very low angle through the atmosphere. This makes the re-entry phase last longer, but keeps the maximum temperature lower. The heat up here is not created by friction. It's a result of compression. The harder you compress the gas, the hotter it gets. So you don't want to bomb straight down. You want to ease in to manage your heat exposure. At T+49:45, we get the call out for peak heating, and we can see the hot gases building up underneath the front wing flap. There's a concentrated flow coming around the bottom near the hinge attachment. We know what happens next. Obviously, that hot gas is desperately in search of a path of least resistance. It doesn't want to get pushed around the flap. It wants to go through the flap. At 51:28, we get a call out that temperatures have stopped increasing. At this point, everything looks really good. We know that the hardware can stand up to the maximum temperature of re-entry. Now it becomes a game of endurance. Not long after this, we start to see sparking, which is not good. Starship doesn't have an ablative heat shield, so it's not supposed to lose anything during re-entry. The sparks are a visual indication that we are shedding material away. When they cut back to the flap view at 53:43, we can already see the buildup of gas is gone from the bottom of the flap. That's because it's found an entry point into the hinge mechanism. Tim Dodd was cool enough to release an interview clip that he did with Elon pre-flight where this exact issue was foreshadowed. Basically, what Elon said was that there is a seal around the hinge that's supposed to prevent gas from coming through, but at the time he was trying to answer the question, does that seal work? It does not. That's not a super big deal though. For additional test flights in the short term, SpaceX can work on a new and improved sealing method. They can iterate. But in the longer term, Elon says that the redesigned ship will move the flaps onto the leeward side or towards the back, away from the belly of the ship. He thinks that this will improve the reliability and also make the vehicle easier to build. We've also got this rendering of Starship V2 from a couple of months ago. Who knows how accurate this is, but we definitely see a change in the forward flap design that looks a lot more pointed, more like a wing and less like a flap. With all of that said, it's doubtful that SpaceX engineers were surprised by the damage to the flap. They seem to have already anticipated this problem and made a solution for it. Elon also posted on X that the front left flap also got very hot but was less damaged than the one that we saw. He says that the rear flaps seem to be okay based on their control authority but probably lost some heat shield tiles. As the atmosphere gets thicker, the most extreme heat has dissipated, but the ambient pressure is now starting to build. Now we're tending with heat and physical force at the same time. This is where things start to come apart at the seams. Coming into minute 56, we see a lot of sparks coming off the body of the Starship. Those are little flakes of material being melted away. When they cut back to the front flap view at 57:16, we can see where a lot of that debris is coming from. The hinge mechanism is definitely compromised, and the flap is being eaten away from the inside out by the heat and pressure of the atmosphere. This goes on for several more minutes. We're all basically on the edge of our seats, waiting for the entire ship to start spinning out of control and breaking apart. Shout out to the live stream hosts here. Oftentimes, they just continue reading their script even when something is very obviously going wrong. Like Starship Flight Number 1, they were still telling us to prepare for stage separation as the vehicle was spinning around out of control. Or on some streams, they just go totally silent when a weird thing happens. But the SpaceX crew stuck with us and improvised, and that was pretty cool. There wasn't really a lot to see after the camera lens got trashed by the debris field from the flap. Not that we really would have seen much anyway. The ship was landing on the night side of the Earth, coming down just west of Australia. We can still kind of get the outline of the flap. I don't know if that's from the residual heat or if there's fire burning somewhere on the body of the ship, or if the camera switched to an infrared view. Either way, we can see the flap moving even though half of it is totally gone. The ship is now stable, and it's in its belly flop skydive position. We're getting prepped for engine relight. This is a really important point that is largely getting overlooked. The engines restarted at 1 hour, 5 minutes, and 41 seconds. These Raptors had been fully shut down, coasting through the vacuum of space for an hour. Then they went through thousands of degrees of reentry heat, and then they successfully reignited. That's a big deal. Raptors may be cantankerous at times, but they are very robust engines. The final test is going to be the relight in a vacuum. If that works, then SpaceX has really made the perfect engine here. As for the landing, the telemetry shows the ship pointed vertical. We can see a sustained bright light on the flap. There doesn't appear to be much relative movement, and then the light fades away, and the nose dips into the water. We get a few more flashes. That's probably the excess methane gas igniting, just like it did under the booster. In an interview with Elon in space after the flight, Elon said that the actual land point of the ship was about 6 kilometers away from the intended target zone. So, do we call that a success? I definitely call it like 99% successful in all regards. The entire ship came back to Earth in a recoverable state. There's a big difference, obviously, between recoverable and reusable. Both the ship and the booster were badly damaged when they splashed down, but they were functional. There's still a long way to go. SpaceX will need to keep doing this kind of flight profile until they manage to recover a ship and booster in pristine condition. They also need to attempt that Raptor relight test in space. If that works, they'll move to a higher altitude that requires a deorbit burn to re-enter. That alone introduces a whole new range of unknown variables. Then they need to send Starship up there with a payload. Then they need to figure out how to deploy a payload. Then orbital docking and propellant transfer, and flying to the moon and landing on the moon. There's still so much work that needs to be finished. What SpaceX has just done is confirmed that the fundamental idea of Starship does work. You can launch a gigantic rocket into space and bring it back down again. That is the hard part. That's the part that no one else has been brave enough to do before. The rest of the job is massive, and it will not go smoothly. There will be much more trial and error. Plenty of error. This will all happen fast, but the final destination is still going to take a lot of time to arrive at. Anyway, the point here is that we have not even begun to see the most exciting moments that Starship has to offer. The best is yet to come.